we now have a way to calculate the dq for a surface charge. Let's go ahead and do it. Let's do a problem. Let's do the charged disk. With charge density sigma, radius r, and let's find the E field at a point. We're going to do a point on the axis of the disk. You'll see what I mean when I draw it. So first, let me draw the disk. Here we go. Nice, big disk. Now this has to be thought of in 3 dimensions. Okay, so this is a disk sort of in the plane of the board. Here's its center, and we're going to put its center on the z-axis coming out this way. So there's the z-axis. We can assume its origin is at the center. Okay. So we're looking for the E field at a point on the origin, or along the z-axis, point P, like that. Okay. So the first thing, like I said, is you got to think about what's your charge density like, what coordinate system you're using. So we're going to use polar coordinates. We have to find a little chunk on this disk that we can describe its dq. So what we're going to think about is some point here on the disk at a radius little r. Okay? So in this case, the total radius of the disk is big R. Often we'll use big letters to mean that's the total, and we use the little letter to mean that's the one that we're going to vary. So there's 2 R's in this problem. There's big R, which I don't want to draw because it'll make the drawing messy. Big R is the radius of the entire disk. Little r is this one that I'm moving around. Okay? So we're going to go and say this is R, and then we're going to move up a little bit and say that's R plus dr right there. So R to R plus dr. And then we're going to move in theta. We're going to go from this point theta to a little point going over theta. So we went R plus dr, and this is theta, where theta would be measured from here. And then we went over to theta plus d theta. Okay? When we do that, we set up a little area. This is our little dq. Okay? Just like we drew it big before. So that's the charge we're going to deal with. Okay? Let's think about the field it's going to create at P. Okay? So first, let's say we now have our charge dq is, like we showed before, sigma r dr d theta. There it is, right there. This is going to make a field. But now, here's the key. We have to use symmetry. Okay? What is symmetry going to tell us? What you have to visualize and think about is the fact that this charge is making a field here. Let me make the z-axis longer to get it out of the way. Okay? So let's think about the dotted line coming all the way from that charge through that point P. We know that it's going to make a field sticking off the z-axis at some angle, like that. Okay? And actually, in this case, it's even more complicated. It's going kind of into the board. All right? But we also know that somewhere else around the sphere, or around the disk, is another charge that would make one pointing like that. And this would make one pointing down, and this would make one pointing up. And those would all cancel. This component of the field for all these different ones would cancel. And you'd only be left with a z component. Okay? So the use symmetry, and what it tells us is all non-z field cancels. So when we do this calculation, we only have to consider the z component. So now we need to go through and think about this angle right here. Oh, okay, so we have a question here. Let me pull this up and see what we got here. Spatially challenged. I need to see it in the VisLab. Okay, so that was a very complicated drawing I did. Okay, let's go look at it in the VisLab. Make sure you get it. Okay, so hopefully that helped. So hopefully that helped you see that this complicated component is sort of sticking off into space, but it'll always be canceled. All we really care about is this component along Z right here. Okay? So the angle between the actual DEP and DEPZ, the one we need, is we're going to call phi. Okay? We can't call it theta. It's not the same as theta. Theta is going around this way, and phi is going around the z-axis. They are different. Okay? So let's see if we can take all that and successfully write the DEP. Let's see. Okay. Coulomb's law, essentially. Ke, Coulomb's constant, times the charge, and I'm going to go ahead and write it this way. Sigma r, don't mix your sigmas and your r's, dr d theta. Okay? So that's dq, that's the charge. And now we need it over the separation squared. So we need it over this line right here. Well, fortunately, that is a right triangle. From here, the dotted line, to this solid line right there, that is actually a 90-degree angle. Between the z-axis and r is 90 degrees. So we do have a right triangle to use where the hypotenuse is going to be the square root of r squared plus z squared, because we're at a point P along the z-axis at a distance z away. All right? So it's getting a little messy in here, but this is r, this is z, therefore those two, or therefore the hypotenuse is the square root of r squared plus z squared. And we need to square it in the bottom. Okay. So there's the bottom. And now we need the z component. Okay? So to get the z component, well, it's like there's some this way, there's some down. It's the cosine of this angle. It's the adjacent, and there's the hypotenuse. So cosine of phi. All right? So that gets us all the way down to that. And then the direction is all we need. Since we called it the z-axis, I'll call it k hat. All right? So there, we've successfully set up the DEP. Now we just have to do the integral.